Yeah, so we will finish up the mass spec today. We're going to just talk a little bit about some alternate ways to ionize samples, and just very briefly talk about some different ways to separate the ions then, so different types of mass spectrometers. This isn't really my strong point, so we're just going to kind of briefly go through these. There is a little bit more information in the text as well. So that'll be the end of this. Then next time on Friday, we will start going through two-dimensional NMR. So again, we'll start out with some theory in the beginning and then introduce experiments and start to practice. All right. Okay, so why do we need alternate ionization methods? So far we've just talked about electron impact ionization. So let's talk first about what are the advantages of electron impact ionization and what are the disadvantages, okay? So for one thing, it's a very sensitive method. We talked about that it's very reproducible, so it's good for searching databases and things like this. Works well on volatile samples, and we can get a lot of structural information because it induces a lot of fragmentation. So what are the disadvantages? And in this case, the disadvantages can also be advantages. It just depends upon your sample, right? So a disadvantage could be that it requires volatile samples. So that means that they have to be reasonably small in molecular weight and usually less polar, because highly polar samples are going to have higher, boiling points and not be able to volatilize as easily. The other potential disadvantage is that it induces significant fragmentation. And we've seen some examples already where we may have a sample that when we analyze it by EI, we don't see the molecular ion, right? And that's going to give us a much bigger challenge if we don't know where to start when we're trying to analyze our sample. And really, in practice, one of the main things we want to find is the molecular ion, and therefore, hopefully, information about the molecular formula. Okay, so what do we need then out of other ionization methods? We would like to be able to analyze samples with higher molecular weights or masses, right? Analyze samples that are more polar. And if you actually add those two together, then what we're really looking at is to be able to analyze samples that are much more non-volatile. Okay? And the main thing here, too, is that we want to be able to see a strong molecular ion. So these don't necessarily have to lead that way because we may have lower mass, samples or less polar, but we don't get a strong molecular ion. So, we want to see that in those situations as well. Okay. All right, so we have some different categories of ionization methods. Electron impact ionization is a gas phase ionization method, so we know we had to volatilize that. We did it under high vacuum, so we only saw unimolecular reactions, and so we essentially evaporate our sample into the ion chamber.
What do you mean by unimolecular reactions? That just the electron is hitting the molecules of interest and
Yeah, unimolecular just means that the rate of whatever fragmentation reaction only depends upon the concentration of the one compound. So we don't want to have intermolecular reactions.
Do we have them or we don't have them?
Not in EI, but that's largely because the way the experiment is designed, right? So we do this under high vacuum, which means that we actually have
almost nothing.
Yeah, almost a lot of space in between, right? And so they're not bumping into each other. That's not always the desired case. So in fact, the next method we'll talk about is called chemical ionization. And in this method, it's still gas phased, but we are going to desire intermolecular reactions because the ionization is going to take place through a reaction like that. In fact, most of these are going to have some kind of intermolecular reactions.
And is it because we don't have vacuum or we have vacuum here?
In these other methods, like chemical ionization, we're going to have more of a partial positive pressure. Right? So really, I think it's only the electron impact where we have a high vacuum, at least in the ionization chamber. Okay, so there's other methods where we don't actually have to volatilize the sample, and these are called either desorption methods or evaporative methods. So under desorption methods, we have fast atom bombardment, or FAB ionization, and also matrix-assisted laser desorption ionization, or MALDI. Okay. And then we'll talk about one evaporative method, and I think this is becoming kind of one of the go-to methods, is the electrospray ionization. Okay, so gas phase ionization. So we did do electrospray. So let's look at chemical ionization. So in chemical ionization, we use some type of reagent gas. So we have another gas that is ionized, and that ionized gas then reacts with your sample to give usually protonated ions. Okay? In this method, like I just mentioned, we have a positive pressure of the reagent gas because we want that reagent gas to react with our analyte. And so we end up with these M+1 ions, right? And because they're M+1, these are even electron ions, right? As opposed to odd electron when we were doing electrospray.
Because there's one more hydrogen.
One more hydrogen, yeah.
So what is the symbol of EE plus?
Even electron.
Oh.
Yeah. All right, so this method gives us a lot less fragmentation. So we would call this a soft ionization method. All right, so here's an example of how this works. So methane is one of the common ones, isobutane, ammonia. There's a number of different reagent gases that you can use. And I think usually the selection of the reagent gas, there's probably a standard usually in some places, but you might just, I think, more or less have trial and error if you need to use something different. Okay, so like I mentioned, the first thing that we do is ionize the reagent gas. Okay, so we're going to shoot it with an electron to give us an odd electron ion of the reagent gas. Okay, and to balance this, we didn't always do this. I can write 2 electrons over here. So this is essentially an electron impact ionization of the reagent gas. So this can fragment in several ways, and some of this chemistry is kind of odd. All right, so it can go to CH2 odd electron ion, so it can lose hydrogen gas. Or it can lose this is more of a normal fragmentation, could give us a methane radical plus a hydrogen atom. Okay, so this would be a normal sigma cleavage. Now, these active species can react together as well because we're under this positive pressure of gas. So other reactions that can take place are the methane radical can react with another methane molecule to, this breaks all of my organic rules, CH5 plus CH3 radical. So I don't know if it's a bond or if it's more of an addict or something like that. CH3 plus can react with a methane to give an ethane, cation plus H2. So we get these various reactions. So what happens then, we have all of these species in there. Let me move this up just a little if I can. And these species can react with our analyte. So
all of them together?
Well, various ones. It's all going to be just competing. Okay, we just got this kind of big mixture of all this stuff going on.
Thermodynamic, which one is more stable and that one will be predominant in the mixture?
I don't know.
Well, and also, because it's such a high energy environment, you wouldn't necessarily...
Right, it's not necessarily a thermodynamic environment, right? We're just creating a very high energy environment, and we want from one of these, we want to transfer a proton. So something, for example, like CH5 plus, you might imagine as being quite a strong acid. So we could draw it like this, M plus CH5 plus is going to give us MH plus CH4. Okay, or what do I have here? Sometimes you can create kind of addicts. So you can add a reagent gas onto the molecular ions. So for example, M plus CH3 plus could go to M, let's see, how do I want to do this? I guess I'm going to draw this as a bond, CH3 plus. That's kind of confusing, though. It looks like I'm subtracting it. It was what I would usually do, but this is called an adduct. So it would be a methyl group higher. So instead of adding a proton, we added a CH3 group. And so for different reagent gases, you can see different addicts in this way. So here... so here we had the methane plus methyl cation plus methane gave us the ethyl cation. We could have an ethyl cation plus a methane to give us the propyl cation. Right? And so we can get those. Okay, so the big advantage to using CI usually is that we have a much better chance of seeing the molecular ion. And when I was, grad school and back then, we oftentimes would get just an EI and a CI, so we'd get that pair of experiments performed. So for example, here's an EI spectrum, looks like similar to what we've done before. We have the M+, this would be the odd electron ion, right? We're seeing a loss of 15 here, right? So we're seeing cleavage like this to give us 180. Do I have that? If we cleave it here, if we didn't have those methoxy groups, it would give us 77, right? But with the two methoxy groups, this gives us 137. So this isn't a bad spectrum because we see the molecular ion. But if we compare this, here's the CI spectrum here with methane as the reagent gas. And whereas we have the 180, now we see a large 181 with no fragment ions. We also see some, and this is even with methane, we see some M+ ethyl cation and some M+ propyl cation. From those reactions, let's go back. Adducts like that down here. But the most important thing is we see a very large M+1. So if we did these two experiments together, we'd say, oh, this looks like the molecular ion, and then we see this big 181, and that would confirm that.
Makes sense.
Okay.
On the bottom one, there's only like the three big peaks, or is it just whitewash the rest?
Yeah, I don't know if it's because, it should be able to show isotopes in there. So I don't know. Because as long as you can get unit mass resolution, you can't run this without having the C13 isotopes and things like that in there.
Right.
So they should, I do believe that they should show up in there.
Okay. I was wondering if
Yeah.
there's some sort of trickery.
No, I don't think so. Yeah.
Okay.
All right, so next time we will start into two-dimensional NMR, and I'll have a problem set for you.
Woo. Deleted the following Friday as well?
Yeah,
Friday?
yeah, I think so.
Great.
All right, so FAB, or fast atom bombardment, this was another way that we used to use a lot for ionizing more polar samples. And so this one does not require a volatile sample at all, because we're not going to try to evaporate it. So what happens is we dissolve our sample in a liquid matrix, something like glycerol or thioglycerol or nitrobenzyl alcohol or this dinitro-threotol, dithiothiotol and dithioerythritol. This was, I think, called the magic bullet. It was like the good combination or something, I guess. So it's good for polar, non-volatile samples and higher molecular weights than what we could do for EI. So what essentially happens in this experiment is that we have our sample dissolved in the matrix here. So it's placed on this, on the tip of this probe, and it's shot with what's called a fast particle beam. And so this is a neutral atom beam. So let's take a look. I gotta make my room up here. So we know already that we can accelerate ions, right, because of the charges and creating voltage. But how do you create a beam of neutral atoms? right? So this is oftentimes xenon or argon atoms.
Just run electricity through it, or ionize it.
You have to ionize it first.
Yeah.
But we don't want an ion beam,
Yeah.
so we have to ionize it, accelerate it, and then neutralize it after it already has its momentum. Okay, so what they do is they take xenon and they shoot this with electrons, creating a molecular ion, essentially, an ion of xenon. They can then accelerate this, right, across a potential, and they shoot it through, I don't know how you generate this, essentially an electron cloud. And as it passes through, it picks up an electron, gives us a neutral xenon that's already has its momentum, so it's already flying in whatever direction we want. Okay, and then we hit that against our sample. And so essentially what we do is we just blast this sample away, and it just creates all kinds of mess, essentially. You know, it could create cations, anions, adducts, matrix ions, all kinds of stuff. But essentially what we then do is we select out the cations, right? We can create a voltage, and then we just select out what we want, okay? And we just accelerate that into our mass spectrometer, our mass analyzer. So we also have the matrix ions in there. And so this matrix is NBA. This is 3-nitrobenzyl alcohol. And in this case, they added some sodium chloride as well. Because you can get, we'll see here, so with the benzyl alcohol, they end up with an M plus H ion. And then they also get an ion that is 22 mass units higher than the MH, right? And because sodium is 23, this ion here is the M sodium plus. And I think that this only, it says we usually do not see sodium adducts of fragment ions. So the fact that we see this 22 mass unit difference tells us that this is the MH plus. So then, in this case, we see what looks like a lot of fragments, but they could be fragments or matrix ions, and they do have like spectra of essentially the background that you would expect for a certain matrix. So for glycerol or for this MBA, and you could identify which ions typically show up there. But you could also have that would be up above though, your sample plus a matrix ion would be up above your molecular ion. But so I think it's a little harder to use these fragment ions for any kind of, structural characterization. So what we're mostly trying to do is generate the molecular ion.
do we know that one's the molecular ion again?
Well, in this case, I guess this difference in 22 here tells us that this peak, this upper one there, because of this difference, is the M plus sodium.
Oh, okay.
And because we usually only see M plus sodium of the molecular ion, then that's one indication. Otherwise, if we didn't see the M plus sodium here, if we hadn't added the sodium chloride, sometimes you can see M plus sodium even if you didn't add it, because it's just kind of ubiquitous in glassware and everywhere else like that too. But otherwise, it would be just like other, experiments, EI and stuff. We'd be looking at the highest molecular weight ion. In this case, because we're adding an H, well, what do we have here? Well, I don't know what this sample is. But see, this is 1192, so I guess what we would think then is because it's an even mass and it's M plus H that it has an odd number of nitrogens in it. But oftentimes we're doing this, it's not a huge mass, but for peptides and things that are more polar and that could have nitrogen in it. Okay, so MALDI is kind of similar, but a little bit different. In this case, what we do is mix the sample up with a solid matrix, and the matrix is vaporized with a laser. And then again, that ionized matrix, can transfer protons and protonate our sample. So usually what they do is they have a laser that's tuned to the absorption maximum of their matrix ion. So here's some common matrices, and notice that they're all benzoic acids, or this is acetophenone, or these cinnamic acids and things like that. So they shoot the sample with the laser where it can absorb, and then I guess in these cases, these are mostly all acidic compounds themselves, right? They got phenols and carboxylic acids, and those can protonate the sample. So again, I think this is kind of a violent situation in here. We just blast these off and make these ions, and then they get accelerated into the mass spectrometer. So this is good for polar, non-volatile samples, and actually they're very good. They oftentimes use this for proteins, so up over 300,000 molecular weight.
Did you find a molecular formula of the proteins, or just the structures based on the fragmentation patterns?
Well, I think oftentimes they're just going for the molecular weight. Though I think you get very high molecular weights, and sometimes it's hard to, get a very high resolution. You don't always get a, atomic formula for something that's that big. But sometimes they can do, I don't know about proteins, but peptides, they can do what they call, tandem or mass spec, right? Where they can select one ion and specifically and then fragment it later. So you could have some kind of substructure of the molecule and then essentially get a mass spectrum of that. Okay, so here's an example of a MALDI of some different proteins. So these aren't, I guess, huge. So 17,000 or something like that, 12,000. But, as opposed to like EI, they're showing some different peaks here, but, those aren't going to be isotopes, right? Because at this mass, those are much bigger than 1 mass unit gaps there. So I don't really know what those are, why you get those. Okay, so the last one we're going to talk about here a little bit is electrospray. And so this is considered an evaporative technique. So we introduce our sample in a solution now, and it is sprayed out of a capillary that has an electric potential across the capillary. And it's also shot out with a nebulizer gas. So it's kind of comes out of the tube with this ionization and with this gas sprayed out. And it starts out by making these kind of bubbles or, groupings of ions. And then they gradually get evaporated. So the solvent gets removed till we get all the way down to where we have these ions over here. So the ions are formed as a charged aerosol, and then the solvent is evaporated. This is a method that can actually form multiple charges on the same molecule, especially if there's multiple, basic positions. And what this does, because we're analyzing, remember, always mass to charge, if that charge is more than 1, then it reduces the overall mass to charge ratio. Okay, so it brings the mass to charge ratio of a big molecule down into a more reasonable size range. So this is also good for large proteins, and it can be used in both positive and negative modes. So down at the bottom, you can't really see it there. This isn't on yours, but I found this article, and I was going to kind of go over some of it, but I think we're not going to. You can look at that on your own. But this is more of a, organics chemist's guide to electrospray. So they talk about ionization. They also talk about some fragmentations and things like that. I kept planning on reading it to the end, and then I kept falling asleep every time I tried. But I think that's some good, because electrospray is a common method now. This would be if you're doing that, this would be a good article to look at. Okay, so here's an example. This is lactose. This is lactose. Down at the bottom is the electrospray, and we see a bunch of very small ions. We don't see any molecular ion up here at all, right? Because with all those alcohols on lactose, this is going to be not very volatile, right? So at the top is the electrospray ionization, and what they are seeing here is M plus 23, which is the sodium addict.
Again, they use sodium.
Yeah, I don't know if they added it. This is from our text, or if it's just extraneous sodium in there. What I don't understand in this is why they're actually seeing an M plus ion. Because just M plus suggests that they're creating some odd electron ion. They're losing an electron, but I don't think that this method has enough energy to do that. Usually you're just either forming this sodium adduct or protonating. So I'm not quite sure how that gets formed. And I don't think you can form this adduct and then lose a neutral sodium to give us the M plus is essentially like a fragment ion. So I'm not quite sure how that one forms. And what these other ones are down here. I tried to figure out whether, those could be fragments at, breaking this disaccharide apart, but I couldn't match those up. Because you can imagine, and maybe they go into this more later in that paper, that if you could protonate, somewhere like this to form your ion, then you could do, reactions could happen wherever you protonate on those oxygens, right? And it'd be easy to imagine, breaking, this apart like this. Here's another example. This is of this peptide, and peptides can fragment in reproducible ways as well. So what they're seeing here is they see the M plus 1 and they see the M plus sodium. And then there's some terminology here. Well, they have with certain types of fragmentation. So here's, the different amino acids, and they have, here's loss of just hydroxide, I guess. Loss of valine, loss of glutamate. Here's M minus, so this is a cleavage at this position. M minus valine and glycine. M minus down here of glutamine and serine. So they're getting structural information in this case, because the main fragments are just losses of these amino acids. So they're kind of getting a sequence data. So here's an example of a protein by electrospray. And so these are all of the same protein with different charges. So here's M plus with a M over 9, essentially, all the way over to M over 22. Right? So if this is, the protein has the mass of almost 17,000, but this has brought it down into the 1900 range, down all the way to like below 800 is the mass to charge ratio. So I think that they can calculate the charges here, the number of charges based upon, I think if you can get the isotope information. Because imagine that usually we would have M and the M plus 1 like this, and this would be a charge of plus 1, but if we had a charge of plus 2, then the M would be like this, and the M plus 1 would be at a half mass unit. Right? Or if you had a M plus 10 over 10, you could have 10 peaks within one mass unit, right? Because it's divided by 10. So I think they can calculate the number of charges based upon something like that, if they have enough resolution, I guess.
It'd be pretty difficult with this one.
Yeah, it might be. Okay, this was an example of an experiment that we tried when we were trying to use this as a method to look at more like extracts, sponge extracts. So we thought, if we could look at and essentially try to ionize any individual components, and so get molecular ions of more than of whatever is in the mixture. But what we had this one major compound called latrunculin A, and we just ended up with these crazy adducts. So here was the M plus sodium. This is like M plus sodium, so it's two molecules together. This was M plus sodium. And I don't know about this next one, if that's just one more up. But we didn't really find what we wanted. But, you can get these kind of adducts like this.
Are these molecules small that they form adducts of each other, or they're so big?
Well, this M plus sodium was at 444. So it's not so big here. But this was by far the major component in this mixture. So I guess it was concentrated enough that it can somehow stick together. Okay, so here's just kind of a summary. So electron impact was the most common one that we did. In each of these, it tells us what kind of ions are formed, sensitivity range, and advantages and disadvantages. Right, so we've talked about some of these advantages. Database searchable, gives us structural information, but the disadvantage is we sometimes don't see the molecular ion. Chemical ionization, the ions M plus 1, M plus, I don't know what, M plus 18. It probably depends upon your reagent gas. 12? 16, because methane is 16. Yeah, so I'm not quite sure what that was. M plus usually present or some adduct of it. It's good for non-volatile, but it gives us, little structural information. This has a few other ones. Field desorption. Here's Fab, M plus matrix, or M plus 1, or M plus a cation, non-volatile. Matrix interference is a disadvantage, and it's difficult to interpret other than the molecular ion. Let's look down to electrospray. So they can get multiple ions, multiple charges. That's the other thing, I guess, is that this evaporative method, this is probably the most common way to actually connect this up to liquid chromatography as well. Multiple charges, blah, 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 little structural information. So I think the most structural information out of all of these is from electron impact, and that's why we went over it first. But the other ways are good ways to get molecular ions. Okay, so let's just briefly go over some of these other ion separation methods. All right, I don't know that I have all of these here. So this is what we looked at before, is essentially a single focusing mass spectrometer. So we use whatever ionization source. I think in some ways you could combine this up with different ionization sources. They get accelerated out of here, and then their trajectory is dependent upon both the acceleration, voltage, and the strength of the magnetic field, right? So we talked about before that mass to charge will tend to curve or be deflected more. Larger mass to charge will be deflected less. And so by varying either the voltage or the magnetic field, you can kind of scan through the mass to charge ratios. You can hook essentially two of these together, and this is oftentimes what they do when they're recording the high resolution mass spec data. So you can have either two magnetic sectors, or this one's an electric sector. So there's an electric field here that deflects the ions, but essentially they just do this twice, and so you get much higher resolution. Okay, the next common one is called a quadrupole mass spectrometer. This might be what the GCMS is here. And in this case, instead of having this long flight tube, they have 4 different rods here that have, I guess, that they have a constant DC voltage across them and then a modified radio frequency as well. And so the ions come from whatever ion source here, they get accelerated, and then depending upon this radio frequency and, well, for a given mass to charge ratio, it takes a specific combination of this DC and AC voltages. So things will kind of, be attracted to one rod and deflected off the other, and so they can vary those to scan through the different mass to charge ratios. So I think the advantage here is that these are relatively small. They're relatively inexpensive. But I think they usually give kind of lower resolution as well. They're also good for LC mass spec or GC mass spec. All right, the next one is called an ion trap. And I think in some cases this ion trap is kind of taken over for the quadrupole. In this case, so here's where the ions come through. They come down this tube, and then there's essentially 3 different electrodes. There's this electrode here in the middle, which is actually a ring. It's like a donut. And then you have these electrodes that cap the ends. So there's 3 different electrodes. And like the name implies, they can kind of trap ions inside here. And apparently there's several different ways that you can run this. You can trap ions above a certain mass. And then you can sequentially eject the ions out to a detector, and so you can scan through them, essentially getting just a normal mass spectrum. Another way is that they can actually select ions within a mass to charge range, all the way down to trapping a single mass to charge, so a single ion in there. So you can do single ion monitoring and things like that. And apparently you can also do something like that as well by selecting a certain mass range. And then once they're trapped in there, you can increase the energy to cause fragmentation. So this is another way to kind of do mass spec. So you can trap a certain ion and then increase its energy till it fragments, and then eject those to the detector. So sometimes if you have more complicated molecules, or like those peptides or things like that, you can trap a fragment ion in there and then fragment it further after that. Okay, so the last one is that I have, I think, of slides here is the time of flight. So this seems like it's usually used with MALDI. And at least intuitively, this is kind of simple. Essentially, I think they oftentimes do this with MALDI here. So matrix-assisted laser desorption. They can, so here's the laser. So you ionize your sample in here. You can accelerate the ions. And then essentially what it does, if you can give all of those ions exactly the same energy, then their velocity is going to be dependent upon their mass to charge ratio. And thus, the time that it takes for them to fly down a tube or to be deflected and fly back this, so the time is directly proportional to the mass to charge ratio. So just however long it takes to fly down there. I think the challenges are they have to, for one thing, they have to be able to start their clock at 0 to measure the time. And apparently that's why they oftentimes use something like MALDI, because it's a pulsed method. So they can shine the laser, and so then they have time 0 right then. And they have to be able to accelerate it, very carefully, apply the exact amount of energy to all the ions. So this is, I think, usually used with large proteins. All right, so here's a summary of some of these. We don't have the double focusing one here, I guess. So magnetic sectors, I guess the sensitivity is low, but you can get high resolution. They're expensive. Usually you have to have these in a mass spec facility or somebody who actually maintains it. Whereas the quadrupole and the ion traps, I think, are much easier to use, and they're much less expensive, and they're more apt to be, just in lab. They don't take an actual facility to operate them, perhaps. The mass ranges here, I guess up to 15,000. So, the mass range also depends a lot on how we generate the ions, but these are the mass ranges that can actually be analyzed by these mass ion analyzers. So, I guess quadrupole, let's see, these aren't that high. Time of flight says unlimited. We didn't talk about Fourier transform. That's another way that you can get very high resolution, very high sensitivity, and essentially it uses a high,
Ion cyclotron.
Yeah, exactly. But they're super expensive and stuff too. Just like NMRs, I guess. All right. So that's my summary of all of that stuff. Yeah.
Why is the time of flight disadvantage very high resolution, or is it not resolution for the res?
High resolution.
Disadvantage. I don't know.
That seems like an advantage.
Right, yeah, why?
Well, it shouldn't have, well, at least what I have written down is the R value is about 1,000, which is not good at all, comparatively to the other mass spec techniques.
You mean so it doesn't have as high a resolution?
It doesn't have high resolution.
Yeah, that's kind of what I thought too, but it says very high resolution. not very high resolution. But I think with these very high masses, you don't necessarily want a high resolution.
Because they're huge, you don't need it.
Yeah, you don't need it, right?
Although reflection time of flight is actually, the resolution's at 20K. So,
Oh, okay.
so
Maybe
might
you
actually-
can.
it might
The reflection
actually-
one, like I showed on there.
Yes, yeah.
It essentially extends the flight tube, I guess. Because I guess, I don't know how long it actually takes.
Depends on the length of the tube.
I know, but how big,
Yeah.
a building size tube or something? All right, so that's everything I got.
I had another question earlier.
Okay, sure.
In the chemical ionization graph that you showed,
Mm-hmm.
I don't remember when that was, but it didn't really seem like there was any isotopic values. It just seemed like there was only major peaks. Is there
It should be able to. Let's see.